We're back now. Okay, sorry for the glitch. So please join. Okay, sorry about the glitch. So let's just wait for. I love you, because. Okay, let's just wait for the others to join in. I had to use my own internet account because the what do you call this Aramco guest account is bad. Okay, who is this? Abdulaziz. Are you even in my? Okay. Okay, so we're back. Okay. So now, is there any question before I proceed? I know it's a lot. It's a mouthful. So you can type in your question before I proceed. While you're having your dinner, your breakfast, or while you're still in your bed. Okay. So there are 13 people now. Mister, can you take what? The register from here. What is register from here? Can you repeat a little? What? Can you just repeat the salt bridge? Okay. 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 So okay, we will do it again. What is the main purpose of KCL? Okay. So is the KCL to balance the charges? Yes, the charges of the solution. Okay. We will go we're gonna go over it again. Okay. Is the KCL to balance the charges correct? Yes. It is used to balance the charges. Okay. Let's do it again, huh? So we need two electrodes. The electrodes are the solid conductor. Remember that. The zinc and the copper are the solid conductors. We need solid conductors, so that's where the electrons will flow. These conductors should be separated and connected by a wire. Why? I told you earlier that we need to separate the reduction from the oxidation so that electrons will flow. Is the arrow always from oxidation to reduction? Yes. Electrons flow from oxidation, the one that is oxidized, to the one that is reduced. Why? Oxidation produced the electron. So electrons will flow where it is produced. And then since reduction, the cathode. So remember, anode, an ox, and a red cat. Anode, oxidation, cathode, reduction. It will always flow from anode to cathode. Oxidation to reduction. Now, each electrode must be placed in a beaker with its own solution. Zinc with zinc 2 plus, copper with copper 2 plus. Okay, of course there are exceptions to that. So there you go. Now, the oxidation process is zinc will turn into zinc 2 plus and 2 electrons. So the zinc will produce the 2 plus into the solution while the electrons flow through the wire. Now the copper is not the one reacting here. Now remember, copper is a product. This is not the reactant. The reactant is here, the copper 2 plus. The copper 2 plus will accept the electron flowing from the wire. They combine together to form copper. In fact, you can replace this copper with anything. Oh, well, not really anything. By a different metal that does not react. Let's say cobalt. Or not cobalt. I mean graphite. You can replace it with platinum, with gold, things that cannot Nice haircut. Okay, so that's it. And then, as I'm saying, this side becomes very positive because you're putting a lot of zinc 2 plus. Remember, zinc nitrate is balanced originally, but as you put more zinc 2 plus, this become very positive. This side become very negative. Does not react with what? With any of them, with the zinc or the copper. Now, because of this, this two, uh, once they're not balanced, like this is more negative than more positive, the electrons will no longer flow. Because electrons, when they see that this becomes very negative, will be repelled. And so what happens, we need to put a salt bridge. The salt bridge is connected to two beakers. It completes the whole circuit. Now, what is the purpose of the salt bridge? To maintain electrical neutrality of your solution, the cathode solution and the anode solution. So because the anode solution become very positive, the chloride will go there, will flow there. Because the cathode solution is very negative, the K plus will go there. That's why cation, that's why we name positive charge ion as cation, because they go to the cathode solution. The anion is called anion because they go to the anode solution. Is zinc 2 plus there initially? Yes. The zinc 2 plus is here initially. But since you're producing more, this become very positive. That's why we're saying this become more positive. Because aside from zinc 2 plus that is already there, and it is balanced by the nitrate, remember, 1 zinc 2 plus, 2 nitrate, it's 0, neutral. But because you're adding more zinc 2 plus and you're not adding nitrate, so it becomes positive. That's why you need to chloride, this one, the salt bridge, must flow here so that it balances the extra zinc 2 plus. Are there any questions before I proceed to the next one? Any question? Are you sure? Why are there 19? I have only 16 students. There are 3 extra people here. Okay. Oh gosh. This is even more tiring. Did you know that? More tiring than the actual one. Clear? Okay, are there any questions before I move on? Okay. Now, one of the things, or just after the reaction, what's it? Or just zinc 2 addition? No, zinc 2 plus is there. Zinc 2 plus is already there, and then you add more because of it. So if the reaction continues, it will stop because there will be not enough zinc. No, the reaction will stop because there will be electrons will not flow anymore. Remember, this is negative. The solution is negative here. Electrons flow to the negative. Oh, negative, it will repel. Okay. That's it. I have other viewers. Okay, are we good? Before I move on, now we have a question here. One question. Okay, thanks. Is zinc added or it is reacted with the solution? You need to be very clear. What's zinc? Are you talking about zinc or zinc 2 plus? Originally, you have a zinc metal solid inside a zinc 2 plus solution, like zinc with zinc 2 plus. Okay. Now, this is zinc nitrate, meaning it's neutral. For every 1 zinc, there's 2 nitrates. So it's neutral. But as the zinc oxidizes, you produce more zinc 2 plus. Therefore, there will be more zinc 2 plus than nitrate. And so the anode solution becomes more positive. Okay. You get the idea? I hope so. Homemade. Is zinc added reactive to the solution? You need to be very clear. Are you sure? Okay. Now, we have a question. I have a question here. Why did the zinc lose electron and not the copper? See, I already talked. I simply told you that the zinc will oxidize. Redox reaction have different tendency to give up electron. Some can easily give up electron very clearly. Some will be more difficult. And so it's a matter of a what you call a comparison. So remember metals, all of these are mostly metals. Metals love to give electrons. But the thing here is that some of them give up electrons much easier than others. And so when you put two metals together, yeah, in a way, it's ionization energy. In a way. Yeah, correct. It's ionization energy. Correct, Mohammed. Some electrons can easily be removed, some cannot. However, here's the trick, Mohammed El Asil, okay? Because you're talking about ionization energy. Ionization energy is measured at very high temperatures. Because for ionization energy is the energy needed to remove an electron from a gaseous atom. That's the difference. Remember that the zinc we're talking about here is in solid form, not gas. So the the ionization energy that we discuss in chapter 7 is actually for a gaseous atom, like zinc gas becoming zinc 2 plus gas. Okay. So ionization energy is strictly defined in a gas phase. Remember that this is solid. Now you might say, okay, I got 2 in AP. Awesome. Okay, I think he was my former student trying to chime in. Maybe he doesn't have any class. Okay. Okay. This is crazy. Okay. Where were we? I got distracted. So, you can liken this to an ionization, but it's not strictly ionization because of the valence electrons. Yeah. The reason. Okay, here's the thing. So why would electrons move? Remember, we already learned who gets to. No, somebody from my class before. He's actually joining us. What do you call this? I got distracted. What am I talking about? Oh yeah. Electrons. See, I got distracted. What am I talking about? I'm getting old. I think I get dementia. What am I talking about? Yeah. The metals have different what do you call this? Different tendency to actually lose electrons. Some ionization energy of solids. You are still young, mister. No, you're still young. No, I'm not. See, I got white hair already. Okay, so metals would have different tendency to give electrons. All of them are metals, so they give up electrons. But some give up electrons more than others. Now, is this about ionization energy? Well, actually, technically, no. Why would electrons move out of zinc going to copper? Why would they do that? Remember that remember you will be engineers in the future. And one of the things that engineers must know is what we call transfer. Energy transfer, mass transfer, meaning transfer of materials and energy. Why would heat flow? Because there's a difference in temperature between two things. Why would mass diffuse? Because there is a difference between low concentration and high concentration. If there's a difference in concentration between two things, they flow. If there's a difference in pressure, they flow. Wind flows because there is a difference in pressure. Why? If there's a difference in temperature, energy flows. So you see, it's all about a difference in something. Okay? Now, here, what is the difference? The difference is what we call potential. Potential difference. The word potential difference is the same word we use for volt. I think you've heard the word volt. Volt is a fancy word for potential difference. There is a difference in potential. It's like, What is the difference in potential? You know, like a difference between, oh, this, like, for example, two student. Oh, this student has a potential to become a 5. This student has a potential to become a 4. Therefore, their potential difference is 1. You understand? There is a potential difference between potential, meaning the ability to. What is the word that written in green in the top right? Oh, zinc and copper electrode. They are called electrodes. Okay. So there is a difference in potential. Now, what I want you to do is to go to your notes, electrochemistry notes. Where's our electrochemistry notes? You go there, and you go to page. What do you call this? Okay, are you with me? Okay, you go to my notes. Okay, you go to my notes and open the notes to page. Page. Where's this? Page 7. This one. Page 7. I hope you can see it well. Okay, is everybody in page 7? Okay, page 7. Okay, now you can see here in page 7, this is what we call a reduction potential table. Reduction potential. What does reduction potential mean? So I'm going to erase this now, huh? What time is it? We can only say until 8:20, isn't it? We have 4 minutes. I'm just going to discuss reduction potential. Then we'll have a little break. I need some break as well. Okay. So what is reduction potential? So, for example, look at this. I'm going to look at the reduction potential of zinc. Zinc becoming zinc plus 2 electrons will give me zinc. And then copper 2 plus 2 electrons will give me copper. Both of these are reduction. Am I right? It is we want a quiz, Mr. Garcia. Zinc 2 plus 2 electrons will give me zinc. That's reduction. Copper 2 plus 2 electrons. That is copper. Okay. Now, here's the thing. You would see there a symbol E naught. E naught is what we call the reduction potential. Reduction potential. Okay, in volts. Now, if you look at this, we look at copper. This one is positive 0.34 volts. And the other one, the zinc, is, where's zinc? Is negative 0.76 volts. Okay. So here, you would notice that you would realize, like, which one has a greater tendency to be reduced? The copper 2 plus or the zinc 2 plus? What do you think? The more positive the voltage, the more it will happen. Remember that. So between copper and zinc, which one will be reduced? Copper. Okay, we have, oh, hold on. We have a problem. Copper, all of you are wrong. It's copper 2 plus. Remember, it's copper 2 plus or zinc 2 plus that are the ones. See? Zinc metal and copper metal, a solid, are products. It is copper 2 plus is the correct answer, not copper. Copper 2 plus. So copper 2 plus is a greater tendency to be reduced and not the zinc 2 plus. Therefore, which one will be oxidized? It's hard to write copper 2 plus. I know. Okay. But okay. So meaning, what will happen to zinc? we need to flip the zinc. Meaning between these two, this one has a greater tendency to happen. So what we do, we flip the zinc. The zinc will become zinc, becoming zinc 2 plus 2 electrons. And the negative 0.76 now becomes positive 0.76 volts. So this will be our reduction, and this will be my oxidation. And and then we added zinc plus copper 2 plus, the 2 electrons will cancel, will give me zinc 2 plus copper. And this gives me an overall cell potential of 1.10 volt. A break time, mister. Okay. So we will continue. We'll end the stream and we'll have 10-minute break. Okay. Thank you. Bye-bye.